Alright, so these are going to be video solutions for Activity 7C out of the ESA Level 3 Physics book. So question 1. An open railway wagon rolls with a negligible friction and vertically falling rain, and a appreciable amount of rain falls into the wagon and accumulates there. By considering conservation of momentum, explain what will happen to the speed of the wagon. Ignore the effect of drops hitting the front of the wagon. So what's going to happen as the rain falls into the wagon is the mass of the wagon will increase. In absence of external force, the momentum is conserved. Okay, so here we're talking about horizontal force, right? Any vertical force from the raindrops is being resisted by the ground, so there's going to be a net. There is no net vertical force and no horizontal force, because the rain's falling vertically, right? So while the rain is falling vertically, there's no horizontal force and there's no net vertical force because of the ground as well. So P is constant. Now P equals mv. Therefore, so momentum equals mass times velocity. If m rises, then v falls. So velocity of the wagon will progressively reduce. B. The rain stops. A drain plug is opened in the bottom of the rolling wagon, allowing the accumulated water to run out. Explain what will happen to the momentum and speed of the rolling wagon plus water within. Okay, so now here's an interesting one, right? The trite answer to this, or the wrong answer to this, would be that the wagon speeds up, because the thing here is that the wagon and all the water have the same velocity. So the water draining has momentum in proportion to its mass. Therefore, what's happening as the water drains out? As water drains out, the momentum is dropping. And the mass is dropping, and the velocity is staying the same for wagon and remaining water. Basically, the water that's falling out is taking with it the momentum, the same momentum that it had while it was in the wagon, because the wagon is travelling forward, but so is the water that's draining out. When the water hits the ground or hits the air and starts to slow down due to air friction, it might slow down to a stop, but it's taken the relevant amount of momentum with it as it's drained out of the wagon. All right, now question 2. In a game of pool, the white ball is hit by the cue and travels with momentum of 0.15 kilogram meters per second left toward a stationary coloured ball of mass of 45 grams. The balls collide, and afterwards, the white ball is travelling at 0.10 kilogram meters per second in the upper left direction. The coloured ball is travelling at right angles to the white ball in the down left direction. Draw a vector to show the total momentum of the two balls after the collision. Well, key principle, absent external force, momentum is conserved. Here, P initial, therefore P initial equals P final, and the total momentum of the two balls after the collision, therefore the P final has to equal the P initial, and the momentum before was an arrow, and the magnitude before was 0.15 kilogram meters per second. So that is also the momentum after. Alright, what's next on the agenda here? Write a vector equation to show how the total momentum is related to the individual momentums of the two balls after the collision. Okay, so the total momentum is related to the two balls. Well, P after equals, we'll call it P white plus P colour. And so we've got, do they actually want us to solve this? I'm not 100% sure. I guess they want us to do a vector equation. So vector diagram. So a vector equation, let's just put arrows over that. Maybe that's all they want. Draw a vector diagram and use it to show that the size of the momentum of the coloured ball after the collision is 0.11 kilogram meters per second. Well, P after is that, and it's 0.15. I'm assuming that the two angles they've given us are at right angles to each other. It's not 100% clear, but what we've got to do is we've got to have this one plus this one from their diagram. The white has gone this way, so this is P white, and this one is P colour, and we think they're at 90 degrees to each other. This one is P, what are we told? The balls collide, the white, afterwards it's travelling with a stationary coloured ball, so PC equals MV, and P white equals M white V white. Now we're given the velocity of the white, 0. Oh, actually, we're given a momentum for the white, so equals 0.10 kilogram meters per second. So 0.10. So now we can work this one out using Pythagoras. So 0.115 squared equals 0.10 squared plus PC squared. PC equals the square root of 0.115 squared plus, minus 0.10 squared equals the square root of 0.115 squared, 0.1 squared equals. Sorry, I've done the classic problem here. That does not exist. I just realized as I was about to stick it in the calculator that I didn't remember having the extra there. So that's a good thing to pick up. So it's 0.15 0.15, 0.15 squared. So, 0.15 squared, I'm pretty sure is 0.22, it's 0.0225 minus 0.01 equals the square root of 0.12125. Square root answer equals 0.1118 or 0.11. Then we were asked to find. Oh, yeah, we've done that. So to two significant figures: kilogram, meters per second. All right, we're getting up to part D. D, calculate the speed of the coloured ball after the collision. Let's just do that up here. D, PC equals MCVC, 0.11 equals 0. And here's the only key question. Convert 45 grams into kilograms, which is 0.045. Times VC equals 0.11 divided by 0.045, which is, and we carried through, what I've tried to do actually in my calculator is I've carried through the extra decimal places to get 2.4845, which is 2.5 meters per second to two significant figures. And part E, calculate the angle through which the white ball was deflected. Well, if we look at these numbers here, we've now got a number here for this. We can use Pythagoras' theorem. We've got, if the white had continued on, it would be there. So we're interested in the angle that the white has deflected. So if we continue that one on out this way, that one on this way, it's this angle here is the deflection, which is the same as that angle there. And so we can use our Pythagoras. So this is the hypotenuse, that is the adjacent. So I'm guessing that, well, I think that cosine of theta equals, I'll just put that on another colour. So if this is theta, then this is the adjacent, and this is the hypotenuse. So cosine of theta equals adjacent over hypotenuse. Cosine of theta, we want that, equals 0.10 divided by 0.15. Theta equals cosine inverse of 0.6667 2/3 equals 48.189 or 48 degrees to two significant figures. And I'll just quickly check that those answers are correct according to the book, and they are correct according to the book. So tick that off. Oh, I'll check out this, what do they want for the momentum equation? Yeah, this is what they had in mind, except that they also actually put some numbers in it. They particularly put the ones they already knew. So, you know, they actually put in that P after was that way 0.15 equals, oh sorry, yeah, that way 0.10 plus that way PC. So they actually went that far in the answers. Hard to say what they're after. If you had written all that and then you got to here, I think you're sorted if this was an exam question, because this embodies that anyway. Okay. All right, question 3. The game of curling is often played on, I made up a curling question, didn't I? On frozen lakes or rivers, and involves sliding large smooth rocks with handles called curling stones along the surface of frozen water toward a target stone called a tee. I didn't know that. Two players are curling on a frozen lake in central Otago. One of the players sends her stone, travelling with a momentum of 47 meters per second, toward her opponent's that way. So let's just draw a diagram as we go. 47 meters per second. This is called stone A. Toward her opponent's stone B in an attempt to knock it out of the way. The two stones collide, causing A to be deflected through 90 degrees. Its momentum after the collision is 8.6 meters per second. Draw a vector diagram to calculate the size of the change in the momentum of stone A. Well, change in anything is the thing equals final minus initial. So delta P equals, P final minus P initial. Now, it was deflected by 90 degrees to go this way, so as that was before. After, A is going this way with a momentum of 8.6 meters per second. We don't really know what's happened to B. We don't know. So the change in momentum for A, delta P, is P final minus P initial. And the thing I like to remember is that that's the same thing as plus negative P initial, because we can do that. Negative P initial is just the same amount but reversed. So that is this 8.6 plus that 47, and if we do that, we go, let's just start over here then, 8.6 plus 47 gives that our change delta P, there it is. There's our change delta P. Were we just asked to do that much? Draw a vector diagram to calculate the size. Oh, we want to calculate the size now. So we can just use Pythagoras. So delta P for the size at least is 8.6 squared plus 47 squared, which is 48 meters per second. Two significant figures. Well, it's only part A. I've already used up a whole big chunk of space. Calculate the size of the momentum of stone B after the collision. Well, there's an interesting aspect, isn't it? So, P tot before equals P total after. Now before, that's that, 47. Now after, we've got A, well, that's that, 8.6 plus PB. Now one thing I can show here is that this is going to be a difference thing again. There's another way to think of this, which is that the change in momentum of stone A equals negative of the change in momentum of stone B. In other words, because the Newton's third law applies for every action force, there is an equal and opposite reaction force, and a change in momentum is based on impulse, so the impulse force. So the impulse on A is the opposite of the impulse on B. So the change in momentum for stone B must be the opposite of this this change in momentum of stone A. So this is exactly what this is going to find is 47 minus 8.6 versus 8.6 minus 47. If you can see it's 47 that way minus 8.6 that way, which is the same as 47 that way plus that, right? Which is what we did over here, except it's exactly the opposite. Both these vectors are in the opposite direction. So if we want the size of the momentum of stone B after the collision, it is 48 kilogram meters per second. And the second thing is explain any assumptions you made. No external force acted on the stones. So that's the key. Right, now what about the next part? Draw a labelled vector, or labelled arrow on a vector diagram to show the direction of the momentum of stone B after the collision. Oh, I've drawn a vector here, but now we've actually got a vector down here, so let's just, we know that it's PB equals 48 kilogram meters per second. We also could work out the angle from this. So this is part C. And D, after the collision, stone A goes on to hit a tree. Alright, stone A goes on to hit a tree. After this collision, stone A and the T, on to hit the T, not a tree. To hit the T after this collision, stone A and the T are travelling at right angles to each other. The T with a momentum of 4.2 kilogram meters per second. Calculate the angle through which stone A is deviated by its collision with the T. So stone A ended up going this way after the collision. So it had a 8.6 kilogram meters per second straight down. And then this is stone A, right? And stone B, and then it collides with the T. And after this, they are travelling at right angles to each other. And the T has a momentum of 4.2 kilogram meters per second. And what we know again is if we assume that no external force, therefore P is conserved, then this one, P A before equals P A after plus P T after. Alright, and we've got that this one, we don't know any angles yet, but we're going to be able to at least make a vector diagram. So this equals this plus that, and they are at right angles to each other because we're told that these two are at right angles to each other. I should have drawn it in there, shouldn't I? And this is 4.2. And we know this one. This was 8.6. We know those two momentums. That's what they've given us. So we can work this one out. This is the square root of 8.6 squared minus 4.2 squared by Pythagoras' theorem, which is 56 square root of that. Uh, 7.5 kilogram meters per second. But we haven't actually been asked for that, have we? We've been asked for calculate the angle through which stone A is deviated. So this is the T, and this is A after. So, and this is A before. So the angle of deviation is that angle there, theta, which is the same in two angles at a point, like two angles where two lines cross. This angle and that angle, the opposite angle, are the same. So we actually just make it a little easier to see that. I'm going to just highlight that here. So this angle here is the same as that angle there, because when two angles come together at a point, that angle and that angle are the same. All right, and if we think about these things here, this is the hypotenuse, this is the adjacent, that's the opposite. I didn't actually even need to calculate the length of this. We could just use the opposite and the hypotenuse to come up with this angle, which is the same as that angle of deviation. If we have we got socket tower, so let's have a look. Alright, so sine of the angle equals the opposite over the adjacent. Those are the two we started with. So we're going to work with that. Sine of theta equals 4.2 over 8.6. Theta equals sine inverse 4.2 divided by 8.6. So I do this my own old school way, so rather than rely on the calculator, 4.2 divided by 8.6, and I could write this down, 0.48837, but then I can actually just go inverse sine answer. So I basically don't rely on the calculators getting the order right. 233 degrees. 29 degrees to two significant figures. Okay, and I will just quickly check those answers to ensure that we are still cracking. We are cracking. Okay. What do we got? Question 4. At a bowling alley, a 6.8 kilogram bowling ball traveling upwards with a momentum of 44 kilogram meters per second hits a stationary pin of mass 3.5 kilograms. After the collision, the bowling ball and pin are moving at right angles to each other. The bowling ball at 5.4 meters per second and the pin in the direction up and to the right. So let's just draw this. So the ball before, the pin, the ball. This is 6.8 kilograms, traveling at 4.2 meters per second, so we can work out a momentum. So it's not, is it? It's 44 meters per second, and hits a stationary pin of mass 3.5 kilograms. After, we've got the bowling ball and the pin are moving at right angles to each other, so we've got the ball, and it's moving at 5.4 meters per second. Still has a mass of 6.8 kilograms, whereas the pin is moving that way, and the angle is a right angle. Okay, so let's just try and remember that. Alright, so that's our core information put into a diagram. A, calculate the momentum of the bowling ball after the collision. Well, are they wanting angles or just a I think they're just wanting at this point a because we're going to get a draw a vector diagram and so on and so on. So let's just start with magnitude. P equals mv equals 5.4 times 6.8, which is 36.72 kilogram meters per second, or what were we given these to? Just two significant figures. 37 meters per second to two significant figures. We'll do part B. Draw a vector to show the size and direction of the total momentum of the bowling ball and pin after the collision. Well, the total momentum after is the same as the total momentum before, right? So P after, P before. Therefore, so the same as this, and the only momentum you had before is this one. So this is, we need the size and direction. Well, the direction is straight up, as I've just drawn it. And if we multiply two together, whoops, 44, and P equals, always write them down, P equals 44, 6.8 times 44, which is 299.2, or 300 kilogram meters per second to two significant figures. Part C. Show that the size of the momentum of the pin after the collision is 24 kilogram meters per second. Oh, you know what? I've got this completely bonkers, haven't I? I've just gone and done a calculation as if this 44 meters per second up here is speed. I'm just looking at this and going, well, hang on, this isn't going to be right because 24 squared and 40, these aren't going to be right. So let's just go back to this one here. I'll just scrub most of this out. The right premise was there. I didn't need to go anywhere near as far as I went, right? Right, so let's go back. So P before equals P after. That's the totals. So the answer to B is simply upwards at 44 kilogram meters per second, because this is the only momentum before, because this one is stationary, so its velocity is 0, so this has no momentum. This has all the momentum, and its total momentum was 44 kilogram meters per second. Okay, that makes better sense. Makes better sense of the next answer. Anyway, show that the size of the momentum of the pin after the collision is 24 kilogram meters per second. Okay, so afterwards, this one and this one have to add up to this one. So this is the resultant P after, and it's 44. And whereas this, we've been given that we've worked out already that P of the ball after is 6.8. Oops. But it's not it's 37. So the momentum of the ball in that direction is 37. And this one is the unknown, P of the pin. So what does it say? Show the size of that. So then we get that we're going to do a squared equals a, b, and c, Pythagoras again. So 37 squared plus pp squared equals 44 squared. pp equals the square root of 44 squared minus 37 squared, which is 23.8117, 24 kilogram meters per second to two significant figures. So you can see how we get to the answer we had to show by doing the rounding. So you've got to show all your working up to the point of having to do the rounding is the way to do those sort of questions. Part D. So part D, calculate the angle through which the bowling ball was deviated by the collision. So this is where we go, okay, it was here. This momentum is now created by the momentum of the ball and the momentum of the pin. Now these two suckers are not the same, well, I assume they're not the same mass. So what have we got to do? Well, we got an angle still. We've still got the angle of the velocity, even like we know the direction of the momentum, and we had the direction of the momentum before. So that's definitely the direction of the velocity. So what we need is this is the angle of deviation, because this was P ball before, and this is P ball after. So this here is the angle of deviation, theta, and the momentum of the ball before was 44. The momentum of the ball after was 37. And we've got this angle theta. We know that this is the hypotenuse, it's the long one. This is the one adjacent, so it's the adjacent, and that is the opposite. So saw ka tor. So saw ka tor, and we've got the angle, we've got the hypotenuse and the adjacent. So cosine of the angle equals the adjacent over the hypotenuse. Cosine of theta equals A over H. And go and get my normal pen colour back. So theta equals cosine inverse 37 divided by 44. Now, probably should have carried through some more stuff, so I'm actually going to use in my calculation this one here, 36.72. Whoops. 36.72 divided by 44, close bracket equals, oh, I see what I'm doing wrong. Hitting the wrong thing. Inverse case properly this time. 37 divided by 44, close bracket equals. Right, I get 32.763, which is 33 degrees to two significant figures. Part E. Explain why the size of the change in momentum of the bowling ball is the same as the answer to C. What? Calculate. Show the size of the momentum of the pin after the collision is. Explain why the size of the change in momentum of the bowling ball is the same. Oh, okay. So it's asking, so this was, part C was the momentum of the pin. And the answer to this is impulse. So according to Newton's third, the force on the pin is equal and opposite the force on the ball. Therefore, the change in momentum of pin is equal and opposite the change in momentum of the ball. And you could go on, if I had more space, and say the change in momentum of the pin is from 0 to 24. The change in momentum of the ball must be the same as that. All right. We want one more. If the bowling ball and pin are in contact with each other for 0.090 seconds, calculate the average size of the force of the bowling ball on the pin. And it says the size of the force, not the rest of it. I'm just going to plug this in up here. Oops, F actually, isn't it? So delta P equals F times delta T, or just FT if you want. So 24 equals F times, and in this case we're given 0.090 seconds. F equals 24 divided by 0.09 equals 270 newtons to two significant figures. I'm just going to quickly check those answers before I move on to the next question. They look about right. All right, and next question. Come on, clear. There we go. Question 5. A rock with mass 31.6 kilograms is precariously balanced on top of a cliff and is in danger of falling. It is decided to blast the rock apart with explosive. The explosion causes the rock to break into 3 pieces, each traveling in a horizontal direction. After the explosion, so we have to think about it, this is top down, I think. After the explosion, yeah, we do. Piece A, so what they're doing by saying horizontal means you don't have to do it in 3 dimensions, right? So the rock before, now after, we've got piece A is traveling north. No, the rock had 31.6 kilograms. Drawing diagrams is a really good way to try and check that you understand a problem. North, it is 7.95 kilograms and it's traveling at 6.75 meters per second. Rock B is traveling west at it weighs 11.6 kilograms, is traveling west at 5.55 meters per second. And somewhere we've got part C traveling somewhere and we have to work out its mass and its velocity. All right, well, the mass is, well, let's do mass to start with, shall we? So, because we can do that without just, so let's just think, I don't even know if we're being asked to specifically, but let's do it anyway. So, mass C equals, now it's just what's left over after this. It broke into 3 pieces, not more. So, 31.6 kilograms minus the mass of A and the mass of B, 7.95. plus 11.6. So if we take those two, the leftover bit is that one. That's what we're after. 31.6 minus 7.95. Right, we get 12.05 kilograms. Okay, and we need the speed of the third piece, C. Well, we can't just add up the magnitudes of these things, can we? We've got to go with it's clearly a conservation of momentum question because there's clearly energy in this explosion. So this had no energy, so we can't do like conservation of energy to find out speeds. We have to do momentum. That means the momentum of A plus the momentum of B plus the momentum of C have to add up to 0. And you'll notice that these two are nicely at right angles to each other. So if we just think about this, we've got to go that, so the momentum before and the momentum after. So firstly, P before, let's just, equals P after, right? Because conservation of momentum. there is an explosion, there is a force acting here, but it's a force that's internal to the object. It's a force that causes the object to shatter, which means that well, this is the way it's supposed to work anyway. It means that this is true because the forces are internal. And so then we go, all right, so 31.6, but it's not going anywhere. So this says momentum before equals m times v equals 0. 0 equals p after. That's the most important thing. So p after equals 0, right? And that means that, therefore, PA plus PB plus PC equals 0. Right? That's what we've got to get to. Vector diagram, A plus B, PA plus PB plus PC have to equal 0. Back to the start, right? That's the key to getting to 0. And now we can make this work. So we need PA equals, and we've got, we're also going to be asked for direction and stuff, so we'll do that as well. But PA equals MAVA equals mass 7.95 times 6.75, which is 53.6625. PB, MBVB, and we're just going to do this one this time. So mass B is 11.6 times VB is 5.55, 64.38. Put some units on, Logan. And so we can now solve for PC by using Pythagoras' theorem. PC squared equals PA squared plus PB squared equals 53.6625 squared plus 64.38 squared equals 7,024. So PC equals the square root of 7,024.44, which is 83.811, blah, 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 blah. It's too many. We don't need that many probably. And if we want to find the magnitude, then PC equals MCVC. So VC equals PC over MC, which is 83.811 ... divided by, and we worked out the mass up the top left there, 12.05. Here it is here, which is 6.95. It's actually 6.96 to 3 significant figures, meters per second. Okay, and we want, that was part A. Now we want part B as well. Part B for this one is calculate the direction of the third piece. Well, the direction of the third piece, it's going to be something degrees below east. It's traveling southeast, but how far southeast? Like, what's its actual bearing? Let's go and just draw on here in a different color for a moment. So this is the angle here that we're going to get, and we're going to say it's something or other south of east. And then we can work it out based on these numbers, right? We've got this one, we got these various numbers. So PB was 64.3 53.38. PA was 53.6625. We can go SOCA TOR. In this case, we've got the adjacent and the opposite, so that's TOR. So tan theta equals TOR opposite, 53.6625, divided by the adjacent, 64.38. Therefore, theta equals, and it's inverse tan of that, so inverse tan, well, shall I write it down? And it would appear to be 39.8 degrees to 3 significant figures. So that's south of east. If you wanted a bearing from north, you'd have to add 90, which would make it 129.8 degrees from north. Just have a quick check. South 50.2 east, or bearing 130. So as I say, if you add 90 to the gate, you get bearing. They've gone south, then east 50 degrees. I've gone east, then south 40 degrees. Same thing. Very, it's exact. 39.8 plus 50.2. So south of east, they've gone east of south. But the reciprocal number. So that's correct. Any questions? Feel free to drop them in the comments.